This last video will cover 2.11 and 2.12. For 2.11, we're now looking at, again, two variables together. What if I want to compare a numeric variable across different levels of a categorical variable? So instead of two numeric variables, I now have one of each type. So first I might, start by summarizing a numeric variable, but then realize, hey, maybe if I also include the categorical variable, I'll have more information and a better understanding of the data. So we're going to switch to a new data set here. This is the mole crab data. So this is data collected by a marine biologist of 832 mole crabs from the Salinas River. So you can see in the data set here, we have the size recorded of the mole crab, and this is in millimeters. So millimeters. And then we have the biological sex recorded as male and female for each of the crabs. And so first we might just want to look at size alone. All right, and so the R code here would be showing again just how we're doing histograms, summary statistics, box plots. We can see the results here, but I also want to switch you over to the R server real quickly. The beginning section here is showing that data. So again, just kind of a reminder of what's happening with RStudio here. Before I can use this data, I need to make sure to read it in. So that's what the first line is doing. In order for that first line of code to work, my mole crab CSV data has to be in my project folder over here. So I can see I have the mole crab CSV data. If you don't have yours in your project, you can grab that from the iLearn page and download it from iLearn and upload it into your project folder. All right, so if I read in the data and then I'm just going to do the initial summaries by highlighting what I want to run and then using that shortcut Control-Enter. Then I can see in my output down below, it gives me a little picture of the data. The R console output gives me that summary information where we had asked it to summarize size. So I can see the mean of 16.69, the min, the max, all the quartiles. And then I can see my graphics. I have the histogram and the box plot that we also see in the class handout. So jumping back to the handout, when I look at the results here, one thing that you notice right away that's a little bit different is that we have this kind of bimodal nature of the data. All right, and so we call this bimodal, meaning that there are two modes or two peaks in the data. All right, the previous graphs that we've seen have not looked that way. They have been unimodal. So unimodal is one peak. And then we could also have multimodal, which is less common, but that would be if I have more than two. And when we look at that, you can see from the line I drew, we're looking at a very general sense, okay? You don't have to go kind of individual box by individual box. We're just looking at the overall trend of how many large peaks there are in the data. And then we have the summary statistics. I could think about plotting the median and the mean here. The median is at 13.7, which is right around here. And the mean is at 16.69, which is up here. So we can see that the mean is quite a bit higher than the median. And this is something that you're going to explore more in your homework and at the end of the packet. But you want to think a little bit about why the mean and the median, when they're both measures of the center of the data, look fairly different here in terms of, it has to do with the way that they're calculated. So we'll come back to that. Now, what I want you to do on the next page is pause for a second and think about this question. What can you see in the histogram that you cannot see in the box plot? All right. So if you just had the box plot, what information would you be missing? So pause and think about that for just a second. Okay, so coming back, it's that bimodality, okay? In the histogram, we can see the bimodal distribution. Okay, the bimodal nature of the data. Okay, and so the two peaks, when we see those peaks, we want to think, hey, why would there be two different peaks in the data? Maybe there's some categorical variable that could explain that relationship. And so this is where we would move from just looking at one numerical variable to now saying, hey, I want to compare a numerical variable across different categories. And the way that we're going to do that visually is with a side-by-side box plot. Okay. We could also kind of overlay or stack two different histograms, but the main method that we're going to use in this class is the side-by-side box plot. So again, I'm comparing a numerical variable across categories. So my categories here in this graph are sex. All right, and then my numerical variable is size. And so now it becomes pretty obvious right away that I have different things going on in terms of size based on whether the crab was classified as male or female. And then I can also look at summary statistics for the size separated out by sex. So when I look at these medians, I can see the 22.6 for females and then the 12.2 for males are pretty different. So let's look briefly about how we do this in R. So going back to the server, the second part of this code chunk here, now I'm including that sex variable and I'm going to summarize sex in a table. That just gives me the counts overall. I've got 375 female crabs and 457 males. But now I'm going to use the by function, and this is where it's going to start to let me separate things out based on a categorical variable in terms of my descriptive statistics. So the first piece of the code here is telling me what variable I want to summarize. I want to summarize the size. Okay. The second thing that I list, sex, is really where I'm saying by. So I want to summarize size by sex, meaning I want to get different summaries separately for each of the sex categories. And then the function that I want to use is the summary function. So for each of these different groups, I want to get that numbered summary for all the categories. So if I run this line, I can see that output. I now have the same data that we saw in the PDF file, where I've got those summary statistics about the size, but separated out for males and females. And then the last code here is creating that box plot that shows the differences in size for the two categories, right? And that's the end of the R code. All right, so pause again and work on these discussion questions about which sex tends to be larger in terms of the average or in terms of the median, and which sex varies more. So pause. All right, coming back, you should have found that the sex that tends to be larger on average is females. And then which sex varies more or has greater dispersion is also females. And I ask you to give two different ways that you can tell this. Right, one is visually. If you look at the box plots, you can just see that the spread of the data for females is larger, where the size ranges from about maybe 11 to 28 or so. But the other way you can tell is looking at the summary statistics. You can compare the min and the max there, or you could actually calculate Q3 minus Q1 for each of the sexes and see that that measure, the interquartile range, looks pretty different for the two variables. All right, and so now we've seen kind of how both numerically and graphically we can compare a numerical variable across different values of a categorical variable. Okay, so just summarizing what we've done in chapter 2, we have used descriptive statistics to summarize data. We have visualized categorical data using bar plots and pie charts. We visualized numeric data with histograms, box plots, and scatter plots. And another thing to keep in mind is that thoughtfully created tables and figures are worth more than 1,000 words. So you could write a whole page describing your data, but one great graph or one great table of summary statistics is going to give you a lot more information very quickly. So this is really powerful in terms of summarizing our data. And I know Dr. Canner also started talking you through kind of the statistical investigative process. And you know that this is kind of one of the first key steps in, after we have our data, what we do with it. We need to explore our data, visualize it, summarize it to kind of get an understanding just the beginnings of what our data can show us. Okay, I want you to pause again for these discussion questions and try to work through some of these answers and then resume. Okay, so the caveat of visualizing numeric data by box plot only. You can't see modality, right? We just talked about that one. Right? Between the mean and the median, which is more sensitive to outliers or affected by outliers? So this is one that I haven't directly talked to you about. But the answer here is going to be the mean. The mean is more sensitive to outliers. So for a quick small example of what's happening here, I want you to just think about the numbers 1, 2, 3, 4, and 5. And then think about the numbers 1, 2, 3, 4, and 50. All right, and figure out what is the median for both of those data sets.
We're going to accept this on behalf.
Sorry. You'll see that the median is 3 for both of them, right? The middle number is 3. So m equals 3 and m equals 3. All right. However, for the second data set, the mean gets much, much higher. Okay, for the first data set, the mean is also going to be 3, but for the second data set, that's not going to be the case. All right, so even I'm going to do this a quick calculation: 1 plus 2 plus 3 plus 4 plus 50, and divide by 5, and you're going to get a mean of 12. Okay, and what's going on here is when I calculate a mean, the mean uses all of the numbers in the data set to figure out a measure of the center. So that 50 is included in my calculation. But the median doesn't care what the actual values of the numbers are, it just cares which one's in the middle, all right? And so the median doesn't care about that maximum being a 50 or a 5. It doesn't matter, the outlier does not affect the median. But the mean is greatly affected by that outlier because the outlier is included in the calculation. So the mean is affected by outliers, all right? Similarly, you could think about this related to the IQR and the standard deviation. The standard deviation uses every single individual data point in the calculation, so it is sensitive to outliers. But the IQR doesn't and uses the quartiles, which also don't care about the actual values of the data, just their placement. And so the IQR is not affected by outliers in the same way that the standard deviation is. Is being sensitive to outliers good or bad? Well, the answer is it depends. It's not really a clear answer on that one. A lot of times when we have strong outliers in the data set, we prefer to summarize our data with the median instead of the mean. For example, if we're looking at income or housing prices or data sets like that are highly skewed, it's often better to report medians than means so that the data isn't overly inflated. But the means are really, really commonly used in statistics to summarize data because they're easy to work with, and they do take into account every data point. So there are pros and cons to both of them, and again, you'll explore that more in your homework. So speaking of, after this section, after 2.12, your homework begins 2.13 through the end of the packet. This is assigned now, and it's due next Thursday, February 6th at 10 a.m. It's going to be the same general setup where you need to submit all of your answers on paper. I'll be grading the paper homework, but for any work that you do in R Markdown, you need to submit the knitted Word file as well as a zipped file of the project for me to be able to view all of your work. All right, that is the end of chapter 2. I will see you in class next week.